All of these are coupled, and pretty much the only way to design them and get all the folds to play together is by following mathematical methods. My professional background is mathematics and physics. I did laser physics for 15 years as a profession. I got my PhD in applied physics. And my job in many cases was to figure out how to describe lasers mathematically. And if I could put my problem into mathematical language, then I could rely on the tools of mathematics to solve those problems and to accomplish the goals. But I also felt like origami would be amenable to that same approach. So I started trying to figure out how to describe origami using the tools of mathematics, and that worked.
I'm sort of fascinated about the math here. Like, it's hard for me to conceive of, like, what does that math look like?
The math comes down to a way of representing a design called a crease pattern. Let me grab a couple of crease patterns.
Okay.
So this is an origami crease pattern. It's a plan for how to fold, in this case, how to fold a scorpion. A really good way of designing something like this is to represent every feature, claw, leg, tail, by a circular region, a circular shape. It's not circular folds, it's an abstract concept that you represent the pattern by a circle, but then you find an arrangement of those circles on the square, like packing balls into a box. So for the scorpion, you've got a long tail. Imagine a big circle, like a big tin can. And the legs are smaller circles, or circles of different sizes. So you've got different smaller cans, and the claws are a couple more circles. And you're going to put them into a square box in such a way that they all fit. So you pack the circles into the box, and the arrangement of those circles tells you the skeleton of the crease pattern. And from that, you can geometrically construct all the crease patterns. You follow rules. Put a line between the center of every pair of circles. And then whenever any two lines meet in a V, you add a fold halfway in between. It's called a ridge fold. And there's similar, more complicated rules for adding more and more lines, but the thing is, it's all step by step. It says if you find this geometric pattern, that tells you where to add the next line. And you go through that process until you've constructed all the lines. And when you're done, you can take away the circles. They were the scaffolding for your pattern. And the pattern of lines that's left are the folds you need to create the shape. And that's what's shown here. And this was probably the biggest revolution in the world of origami design, was if you followed that systematic process, the fold pattern would give you the exact shape that you set out to fold to begin with. This circle packing method that I described, this works for anything that can be represented as a stick figure. Like a scorpion, you could draw this as a stick figure with a line for the body and tail, lines for each of the legs, lines for the claws. And from that stick figure, from any stick figure, you can use circle packing and get a shape that folds it. But suppose the thing you're folding is not a stick figure. Suppose it's something that's more like a surface, like a sphere, or or a cloud, or just in animal terms, a big blobby body like an elephant. Stick figure algorithm is not going to work, but there are other algorithms for that. About 10 years ago, a Japanese mathematician named Tomohiro Tachi developed an algorithm that works for any surface. You give it a triangulated surface as a mathematical description, and he will give you, or his algorithm will give you, the folding pattern that folds into that surface. It's now quite famous, and it's called Origamizer. And that is a way you could make a sheet of anything and take on any three-dimensional shape.
So origami is useful in engineering because it provides a method of taking a flat sheet of material and forming it into virtually any shape by folding. Or if the end product is flat, origami offers a way to reduce its dimensions while still deploying easily. The simple act of folding can increase rigidity. Or origami can take advantage of the flexibility of materials to create specific motions. and its principles are scalable, enabling the miniaturization of devices. Perhaps most of all, origami allows engineers to piggyback on the bright ideas people have had over the centuries while experimenting with folding paper. But translating these ideas into practical solutions requires a lot of math, modeling, and experimentation.